All right, guys, welcome to another episode of Cuda Education. Today we are going to discuss the code part of Semaphores discussion. So, this is the Vulkan API discussion series. I did Semaphores part one, which was discussing some concepts on the whiteboard. And then now, what we're going to do is we're going to move into actually seeing this stuff on in the code itself for compute cloth. Again, you guys want to join in on the fun. Tutorial number 1 and tutorial number 13. Tutorial number 1 is to install Vulkan API, and tutorial number 13 is to install all of these examples that you see over here. But we're focusing on compute cloth. Okay, so I just wanted to quickly go through the concepts that we discussed on the whiteboard in the previous video. So I guess I'll just search for semaphore, and we'll go from there. So all right, on line 55 through 59, we initialize a ready and a complete VK semaphore, right? So these are our two kind of flags, and they're named semaphores, right? So we do good housekeeping. So we also have we destroy the semaphores upon cleanup, when the destructor, when we're cleaning up everything. That's pretty straightforward. So we create the semaphores for we actually initialize them now. So that was just a struct before, but we initialize compute.semaphores ready, compute.semaphores complete, right? And if you guys ever want to dive into, a lot of this code is encapsulated, but you could always right click and go to definition or go to declaration, peak definition, to see exactly how it was built. But remember, we have we have computation we have to do, and we have graphics work we have to do. The big synchronization step is, the major one is handing off between compute and graphics, right? So, right, number 1 was compute commands, and number 2 was graphics commands. You could check the previous video for information on that. So let us just continue. So we also had the concept of the first draw, but we'll get into that later. But one of the things that we do here specifically is we're going to wait on compute semaphores to be ready. Compute.semaphores, we're going to wait for it to be ready. So we're not going to do anything in terms of the compute side until we know that everything else is done and it's ready, right? And once the compute stuff is done, we're going to signal for it to be complete. So remember, we had the wait. There were two semaphore flags, or two semaphore stages. There is a wait and there's a signal. So we wait for it to be ready so that we could proceed with the computation. And then upon completion of the computation, we have P signal semaphores, compute semaphores complete, right? So you understand now, you have ready and you have complete, right? So we wait for it to be ready so we could start our computation, and then upon completion, we signal the flag compute.semaphores.complete, right? The next portion of work is that, so we this is sort of focusing on the compute side, but then we also have to worry about the graphics side. So the graphics side is the presentation side, what we see on the screen at the end of the swap chain. When we're actually presentation, we present to the computer monitor, so our eyeballs can see what is being what is being animated, what is being offered or rendered from the application. So again, we have a wait and we have a signal. So the wait, we'll just focus on the compute side. So we're going to wait for compute to be complete. Okay, so we're going to wait for compute to be complete, and then we're also going to signal upon the graphics work being completed. We're gonna raise the flag that compute.semaphores is ready. So what does ready mean? It means that we're done with the graphics work and we could proceed with computation again. Notice that this compute.semaphores.ready is the same one as the one up here. So you signal that you've completed the graphics work. So, you know, compute semaphores.ready. You signal that you have completed the graphics work. And here in this logic, in the compute logic, you're waiting for basically that signal. You're waiting for the compute. You're waiting for the graphic stuff to be complete and for this flag to be raised so that you can proceed with your compute stuff. Let me repeat. We're down in the graphics side of the equation, right? We wait for compute to be complete so we can proceed with the graphics. But then upon completion of the graphics, we signal the compute.semaphores.ready to basically signify that graphics work is complete. Notice that graphics work being completed is the same thing that the compute side is waiting for. They're waiting for this ready flag, which signifies that the graphics work is complete and you can now proceed with your compute side. Upon completion of the compute, you get compute.complete, right? Semaphores complete. The graphics side is waiting for that completion flag, right? It's waiting for the compute complete flag so that the graphics side can can proceed. Upon completion of the graphics work, we raise the ready flag again, and you just go back and forth, right? So that is basically the line of logic that we're following here with all of this stuff. I'll get back to the first draw stuff in a second. Now, we also had another issue that we discussed on the whiteboard, which is present complete and render complete. Okay, so we're just dealing with the graphics side now. So when you're trying to submit graphics commands and do the graphics works, do the rendering, do the drawing, all that stuff, you want to make sure that you're not doing it while you're presenting to the screen. So there's two distinctions. There's presenting to the screen and there's actually rendering or drawing. So you're putting together your vertices, you're connecting the lines of your vertices, you're applying color, applying texture, applying the pictures, the logo, whatever. You're drawing the images, right? That's one step, and the other step is actually presenting to the screen. So in this graphics command section here, you don't want to be drawing or rendering or attempting to render if you're presenting to the screen. So that's why on the wait side, on the wait semaphores, we have two things we're waiting on. We're waiting for the presentation stuff to be complete so that there's nothing we're presenting, at least in this particular situation, we're not presenting it to the screen. And then of course, we also want to make sure that the compute side of the stuff is done, right? So these are wait. So we're waiting on these things. Now the signal side is the opposite side of the equation. We're now signaling that rendering is complete. So we've done the graphics work. We've done putting together the vertices and the pictures and the textures and all that stuff. Render is complete, right? And then of course we're signaling now that compute can proceed because we're done with the graphics work. So we'll run through it again. We wait to make sure that there's no presentation happening on the screen for this particular situation, and we also wait to make sure that we're done with compute work. This is when we're waiting on stuff to proceed with the graphics commands. Upon completion of the graphics command, we signal that the rendering is complete, and we also signal that compute can now proceed because graphics is complete, right? So that's basically the heart of this stuff. And notice that you could wait on multiple stuff and you could signal multiple stuff, right? So all of this kind of works in tandem together to make sure one doesn't get in the way of the other, right? We also have these stages that we discussed on the whiteboard briefly, but basically Um, this wait destinations stage mask, basically it's specific sections of the pipeline. So we're not locking down the whole graphics pipeline and slowing down our application. We're only locking down specific stages. So all of these things have to, you have to wait at specific stages of the pipeline. So everything else that's not relevant to this work can proceed on the pipeline, but when you get to this piece of it, you have to wait until this is complete before you proceed. So you have it for the graphics side of the equation right here, and you have it for the compute side, right? So we're waiting right here, right? So this and this is one thing, this and this is another thing. Pipeline submit pipeline stages. Haven't really dived into that yet, but I will maybe in a future video. But yeah, you notice that you have the VK pipeline stage vertex input bit and VK pipeline stage compute shader bit. You could Google these things to get more information, but it's stages of the pipeline, and you just want to synchronize for that specific piece. Because that's what all of these things are dealing with. Let's see. So again, if you guys, yeah, so that's pretty much it. Let me see. And then we start over. So we build our strut again, and then we make sure we do the destroy the stuff. We actually create the semaphores here. Ready and complete. And notice really that, I mean, for the actual semaphore, we're really just juggling the compute complete and ready, right? I mean, obviously we have the present complete and render complete, but it's really the compute complete and compute ready that we're juggling, because we're trying to manage a handoff between compute and graphics, right? These two commands right here, VK submit, Q submit, right? So everything else before this is we're just loading up the info. We're encapsulating stuff into info, but nothing really happens until this VKQ submit. Okay, so VKQ submit is where we actually submit everything to the queue, and now it's official. Same thing here, VKQ submit, right? All of this is just text on the screen, and we're just arranging stuff and loading up stuff, but nothing really happens until this command occurs, right? Now, I am going to tinker with this in a second towards the end of the video, just to show you something that's really important with these things. Actually, you know what? Let me, well, just give me a minute, and we'll tinker with these things, and I'll show you something that proves to you that nothing really happens until these commands are submitted. I did want to discuss the first draw situation. So in the whiteboard, in the previous video, we talked about first draw. So the very first time that you draw, the first time you call this draw function, you initialize a variable first draw, you set it to true, and very importantly, you mark it as static. A lot of people know more about this keyword than I do, but basically what it means is that this variable is persistent across multiple calls to the function. So it's not like every time you call the draw function, you're going to be reinitializing first draw to true. No. All this static means is that this first draw variable persists along with subsequent calls to draw. That's number one. Number two, you're not reinitializing every time you call draw. You initialize one time, and the variable persists based on whatever changes you've made in your code going forward. So That was a little confusing for me. Some people might not realize this, but so we initialize on the very first call to draw, we initialize this first draw variable, we set it to true, and it's static. On the very first call, this if statement fails. So we're basically skipping out the synchronization semaphore logic for the compute side of the equation. And it makes sense because it's the very first time we're drawing. So, nothing is happening before it. So we don't have to worry about anything. It's like we're driving on a straight road and we could floor the gas. We don't have to worry about, any turns or any obstacles or whatever. We could just skip this logic because it's the very first time we're drawing. However, notice in the else statement, so this piece fails, but then now we update first draw to false, which makes sense because after we run this, after we go through this the first time, now it's no longer first draw. It's going to be second draw, third draw, fourth draw, fifth draw. So this we update the first draw to false. And then we do our, we make sure we have our signaling because we still need to make sure we signal. And of course, we still need to submit queue submit. We still need to run our important function right here to actually submit everything. But notice that for the waiting piece of the equation, we ignore it for the very first draw because, we're not waiting on anything. It's the very first time. But then we still have to put in our signal information and then submit it. Now, on the second iteration, of course, it will go through the graphics and everything too. But on the second iteration, this piece is ignored because first draw is already created and this thing is ignored. So, on the second iteration, we know that from the first iteration, first draw was updated to false. So because this is false, not false is true. So then because it's true, this logic is run. And when this logic is run, now we have to make sure we wait for compute to be ready. And remember, we're going to wait for compute to be ready based on this flag down here in the graphics piece, right? So on the second iteration, we're going to be waiting for stuff. We're still going to be signaling stuff. And then we have our function that we submit, the VKQ submit to make sure everything is official. And that's first draw. But that static thing is you have to be careful of that. So it's making sure that subsequent calls to the same function doesn't throw you off or manipulate this again. And draw is called under the render function, but we're not going to get into that right now, right? So. Okay, all right. So that's basically first draw. That's basically semaphores. Now the only other thing I wanted to do was I wanted to comment out. So of course, when we're running our we have our thing here. So when we're running our application. When we're running our application, we have, this is what happens, right? We have our graphics, we have our computation. You need the computation to know, how the pixels and the graphics are going to change. You see, we put on wind and everything, and that's computation and graphics again, right? But okay. So now what I'm going to do, and I know the author of the code probably doesn't like this, but it's just because we're trying to learn stuff. I'm going to comment out the compute submission. So I'm going to comment out the compute submission. I'm going to rebuild everything. And then so we comment out the compute side, right? So with the VKQ submit, for the compute stuff, we're commenting it out, okay? So we're not calculating anything. We're only doing graphics. All right, so can you guys guess what's going to happen when we do that? You will see in a moment. All right, so now we're going to run our code again. Where are you? Where are you? Okay. And when we run it, we basically we see graphics. All right, we see graphics, but nothing's happening. Right? It's just graphics, and that's it. I don't know if I simulate wind, does it do anything? No, it doesn't do anything. We just see graphics. There is no computation happening, no cloth falling on the ball, nothing. It's just there. Okay? All right, fair. You guys see that. All right, so now let's reintroduce back the compute stuff, but then we're gonna comment out the graphics submission. Okay? So can you guys guess what's gonna happen with this one? Can you guys guess what's gonna happen with this one? So let's we're gonna rebuild it, and then we're gonna run it, and then we're gonna see what happens. If we take out the graphics piece, what happens? Any guesses? All right, so let's run our thing now. All right, what do we get? We basically get a blank screen. We don't even get the menu or anything. All right, and that sort of makes sense because we are not, we're not doing any graphics work. Okay, so you guys see that I'm not just, this is not just smoke and magic. This stuff is actually doing stuff, and even though we outlaid everything here, if you don't submit this VKQ submit thing, you're not gonna get what you want. So a lot of Vulkan is this info stuff. It's like just putting in all the options that you want. Remember, Vulkan is a very granular language. It's very powerful. It allows you to control and do each and everything, which is a good thing because you have control, but it's a bad thing because you actually have to write out exactly what you want. So I did do one other thing, which was like a tinkering with the code and experiment. I wanted to see if the submission order of this stuff would affect the code. This stuff is very involved and it's a lot of moving parts. But I wanted to see if I change the submission order of this, would it affect the code, or would everything still basically line up the way that we expected it to? And we're gonna see. So basically, nothing changed. All right, so there's no it doesn't really affect anything. It doesn't really affect anything, right? But so yeah, and people would know more about why that is than I do. But basically, you submit all your instructions, and it generally, even if you submit it in the wrong order, it generally holds true to what you intend to happen, right? And that's it, guys. That's the Semaphores piece for this compute cloth algorithm. Again, guys, running code on your machine, Windows machine, Vulkan capable GPU. If you guys want to have these examples running on your machine and actively start learning and manipulating and coding stuff in the Vulkan API, I think I have the best approach to this. You could, of course, dive into the spec once you have the code running, change things around, manipulate things, and see how it affects your program. But I will have links down below for tutorial number 1 to install the Vulkan API, tutorial number 13 to install these examples. I have a whole bunch of other tutorials that discuss other specific topics, but I hope this helps you guys. I think this is time well spent. Computer graphics is the future. We're all going digital now, so it's only good things happening from here on out. Thank you guys for watching. Have a great day.